Good day, grade 8 learners. My surname is Botha and I will be responsible for today's natural sciences lesson on electricity. So today we're going to revise electrical circuits and the different symbols that are used in an electrical circuit. We're also going to look at the effect of electrical current and more especially the heating effect of electrical current. Now learners, before you look at electrical circuits, series and parallel circuits and so forth, it's very important for you to know the different symbols that are used in an electrical circuit when we draw electrical circuits. And in your subject guide, which I think all of you received, on page 57, there is this very nice table with all the different electrical circuit symbols together with the function. So it's very important for you to study all these symbols and the functions before you go further, or before you go and draw the circuit diagrams. I'm going to put this away. Let us look at a very simple electrical circuit diagram and all the different symbols that are used. When we look at these symbols, we can see there's two cells represented here, and a cell, when you purchase a battery cell, it looks like this. It's got indication of polarity. There's a positive, there's a negative. Here's another cell, a positive and a negative. There you can see when we join the two and make them work together in series, then we call this a battery. So a single one is a cell, and when they work together, we talk about a battery. Right, now what is the function of the cells and the batteries? These are sources of chemical energy. And what happens is this chemical energy, when we close the switch, the chemical energy is converted to electrical energy. And then the current can start to flow. I'm just going to indicate it with an arrow. This is of course conventional current. So the current will flow. I'm going to draw the current with these little circles, just indicating to you that that is current or charges which carries energy, which are flowing now through this circuit. What we have here is an ammeter. An ammeter just measures the strength of the current, or how many of these charges passes a certain point at a certain time, meaning how quickly or how fast the charges are moving. And the unit that an ammeter is using to measure the speed at which these charges are moving is ampere. Then we've got a switch. At the moment it's an open switch. You can also close the switch. Then a closed switch is drawn like this. That will allow the current to pass, and then the current will pass through the two bulbs. We know what the bulbs are, and what happens in the bulbs when the current passes through the bulbs. They give off light energy. I'll just indicate it like this. So what actually happens is the electrical energy which is carried by these charges are converted to primarily light energy, which is useful energy. I'll write here light energy, which is the useful energy. Of course, we know the bulbs also get a little bit warm, and that is heat energy. And in this instance, heat energy is not useful energy. A bulb is designed for us to give light energy, which is the useful energy, but the little bit of heat energy which is given off. When you touch the bulb, you'll feel the bulb gets warm. Let me show you a little bulb. This is the normal torch bulb. All of you know torch bulb. If the torch bulb was on for a long time, don't touch it with your hand. It can get extremely hot. But what we need to get from a torch bulb is light energy primarily, and we call that light energy, which is useful energy. The heat energy in this case is not useful. So then the charges carry on moving. It also passes through this little bulb, and that bulb also gives off light energy, and then the charges move back to our cells, where the cells supply the charges with more energy, and then the charges exit this side, and then the whole cycle can just go on, and more energy will be liberated or will be converted here from electrical energy to light energy, and that can continue on until eventually later on, it might take a few hours or days, until all the energy, the chemical energy in the batteries or the cells was used up, and then the process stops and we don't get any more light energy from the bulbs. Okay, learners, so now here we have an actual series circuit. When we look at the circuit, you'll see over here we've got 1, 2, 3 cells which are joined together forming a battery, and it is in series. Here we have got a switch, here we've got our ammeter, and then here we've got one bulb. So if I was to press the switch, what will happen? Current will start to flow here from this pole of the battery, conventional current through this black wire, through the switch. It will pass through the ammeter, then it will pass through the bulb, and the bulb is supposed to give us or to convert some of this electrical energy to light energy, and then the current will carry on without really having much energy but returning back to the cells, and this is where the current again will get new energy. Energy conversion is from chemical energy to electrical in here, and then the process will repeat itself through the ammeter again, through here and back. So let us press the switch and see what happens. I want you also to look at what happens on the ammeter when I'm going to press the switch. So pressing the switch, first thing that we can see over here, the light bulb shines, so light energy is given off. The moment I can still touch it, it's not warm yet, but it will warm up quick. And very important, look at our ammeter reading. It's at the moment at 300 milliampere. If I leave the switch, look at the needle. I'm going to press it again. So it's 300 milliampere. Right. Now what I'm going to do is now I'm going to put another bulb in series with the first bulb. There we go. And I'm going to press the switch again, and you must notice what happened to the ammeter reading and also with the brightness of the two bulbs. You can see the bulbs are a lot dimmer, and now the ammeter reading has dropped to 200 milliampere. So the current is smaller, indicating to us that the total resistance of the circuit has increased when we've put in another bulb in series. That's very important. If the total resistance increase, then the total current will decrease. Right. Last thing that I'm going to show to you is what they call a short circuit. Now a short circuit is actually a problem in a circuit diagram. That is when something goes wrong. I'm going to connect this wire over here. There you can see this black wire. Then I'm going to press the switch. You can see my two bulbs, and then I'm going to connect this wire. See what my hand does, and look at the brightness of the bulbs. When I connect that one, what happened? This bulb stopped burning, and that bulb started to burn much brighter. We're going to explain what happened here right now. I'm going to disconnect it. These are two bulbs. The moment when I connect this, the one bulb stopped burning. That one is much brighter. You can also notice what happened to the ammeter reading. When the two bulbs are there shining not very bright, it's 200 milliampere. When I connect this, the ammeter reading increased. right? And the bulb, this bulb was a lot brighter and that one stopped functioning. Right, to explain the short circuit, I've drawn this simple series circuit diagram. It's the same diagram that represents the circuit that we just saw before this. We can see it's a series circuit. When we close the switch, these two bulbs will burn or shine. Now, short circuits happen mostly by mistake or by fault, and that is when if you connect a wire like this, see what happens. The current comes along this conducting wire through the ammeter, through the switch, and when it reaches this point, there's two pathways for the current to go. The one pathway is through the bulb, and this is the other pathway. Now, the top pathway has got very to almost non-resistance because it's just a normal wire, mostly made of copper. So what happens? All of the current chooses the path of least resistance. So the current will flow through that pathway or that wire. And almost none, or we can assume that none of the current will take this pathway because there's a bulb there. The bulb has got resistance, so it's more difficult for the current to pass through the bulb than it is for the current to take this pathway, which has got almost no resistance. So the current will take this pathway, then it will come along here. Here it's got no option, there's no additional pathway. The current now has to pass through this bulb, and it passes through the bulb. Light energy is given off, and then it returns back to the cell. So the moment you turn on the switch and there is a short circuit like this, the current will take this path of short circuit. This bulb will not shine anymore. All the current will go through here and it will return back to the cells there. One of the dangers when this happens is that when this bulb is no more functioning, then the overall resistance of the circuit is a lot less. That's why this bulb is now shining a lot more brighter. But you can imagine that if the current increases to such an extent that it exceeds the amount of current that this bulb can actually handle, then this bulb will burn off. Let me use another example to show you this. So before we go deeper into the short circuit, I think this is a good opportunity for me to explain to you the function of a fuse in a circuit diagram. The symbol that we use for a fuse in a circuit diagram looks like this. I've brought along a fuse to show you. A fuse is just a glass casing with a heating wire in the casing. Now, a fuse is designed in such a way that that little heating wire will burn off the moment that the current that flows through the fuse exceeds the maximum amount of current that it was designed to allow to flow through. So for instance, let's say this fuse was designed to withstand a maximum current of 2 ampere, and now the current that flows through the fuse exceeds the 2 ampere, something like 2.5 ampere or 3 ampere. Then this little heating wire inside the fuse will burn off, the current will stop flowing, and in doing so it might happen that it will protect the remaining circuit components from overcurrent, which might damage them. So in this example that I've drawn here, you can see I've got many cells there. There's 3 globes here. If we keep on adding cells in series, then the total current will also increase. And then at some stage, it will exceed the minimum or the maximum amount of current that the fuse can carry, and then the fuse will burn off. And it will stop the current, and then these globes will not be damaged. So it's actually a very valuable circuit component to include inside a circuit. It can protect the circuit components. Right. I've also indicated it here like this. You can see here I've drawn the fuse with the heating wire broken or burnt off, and then labeling it here, I've said the heating wire of a fuse will burn off if the current exceeds the maximum amount of current that it can handle, and in doing so protecting the electrical component. So this is a valuable, very valuable component. Returning to the short circuit, which I've indicated earlier, if this is our circuit diagram with the many cells, we've got three bulbs there, all of them at the moment is giving off light energy, and if there is a short circuit, let's say there's a short circuit happening there, that can be through fault inside let's say a television or a radio, and there's some of the wires that burns off, and then there's a wire that drops, and it short circuits one of the components like this. Then we know that the current flowing has, at this branch here, it's got two options. It can either go through the bulb or it can go through the short circuit, but because the short circuit has got such a low resistance, it will obviously opt to go via this route. So the current will go in this wire, the short circuit wire. Here now it will carry on through these two bulbs. This bulb will not function anymore because it's been skipped via that short circuit. These two bulbs will shine a lot more brighter because they get a much bigger current. And why do they get a big current? If this bulb is not part of the circuit anymore, only these two bulbs, then the overall resistance of the circuit is lower. And when the overall circuit resistance is lower, then the total current moving through the circuit is a lot higher. And when the bulbs receive a higher current, more energy will be converted from electrical to light energy. They will shine brighter. But the problem is, learners, if this current is now exceeding what this fuse can carry, then the fuse will burn off and it will stop the current from flowing. So it will actually protect these two bulbs from overcurrent. Overcurrent meaning that the current might even be too high for the bulbs to carry, and then the bulbs can burn off, and that can be costly. So the little fuse, this little protecting device, is relatively cheap. It's maybe R1 or R2 to buy a fuse like this, and the fuse can protect all other components. In this case it is two bulbs, but it can be expensive components that can be protected by this fuse. It's a very valuable protecting device in a series circuit. How does it function? It functions by when there's a current flowing through the fuse that exceeds the maximum amount of current for which it was designed, it will burn off, and in doing so it can protect the circuit components that follows.